So while the presentation is being put up there, oh, there it is. I would like to say that when I was an undergraduate student in Novosibirsk, that was then the Soviet Union, in the early 80s, I was studying atomic physics using these beautiful ICAP proceeding books. And at that time, I had a dream that I thought that would never come true, that I would one day attend ICAP, and that was totally forbidden even to think about it. I thought maybe if I'm really lucky, I will get to speak at ICAP. And so I would like to thank the organizers for making this dream come true. So today, I would like to talk about searching for ultralight dark matter with nuclear resonance and atomic spectroscopy. Okay, let me see. My plan is to give a little bit of an introduction for atomic physics audience about what axions and axion-like particles are. And then I will give you sort of a map of experimental landscape, how people look for axions. And then I'll move on to discuss some of the experiments that we are doing. There's a cosmic axion spin precession experiment, or Casper, and another experiment called Global Network of Optical Magnetometers for Exotic Physics Searches, or GNOME. And then I will speak a little bit about some other potential candidates for dark matter, dilatons, and how we look for them using dysprosium atoms. And then I'll tell you about the most recent experiments, as recent as last week, I should say. The paper was put on the archive then. And then finally, maybe I'll make some remarks about some new motivations for doing sort of classical kind of atomic physics experiments that are motivated by these dark matter searches. So axions were introduced in the 70s in order to clean up a lot of problems in particle physics. So actually, the origin of the name has to do with Frank Wilczek, I think, and also the fact that axion is a popular cleaning solution. So if you want to clean out problems, you use an axion. So the one problem, the main problem that it was introduced to solve is the strong CP problem, which is, I guess, a big problem for our previous speaker, that the electric dipole moments of particles are very small, whereas in the case, at least, of the nuclear moments, it is possible in the standard model to accommodate pretty large violations, but they are not seen somehow. And so, oh, sorry. Now, it turns out that in addition to their original motivation, axions are very nice and natural candidates to explain what dark matter is and what dark energy is. But in addition, because they have something to do with CP violation, they may help us also understand the problem of baryon asymmetry, matter-antimatter asymmetry of the universe, and many other things, like, for example, the origin of the hierarchy, which is basically why the masses of particles, including the heaviest particles that we know, are so much smaller than the natural scales of physics, like the grand unification theory or the Planck mass, for example. Anyway, how do people search for axions and more generally axion-like particles or ALPS? Now, we don't, this is a little bit of a funny terminology here, because we don't really need to search for them. We just look in the sky and we see that there is a lot of dark matter and dark energy, so we know it's there. What we mean by searches is that we would like to understand what these things are. So we would like to detect these things by something other than gravity. And so we need to think of what interaction in addition to gravity these particles can have. Okay, and so particle physicists write their Lagrangians, and there are various terms in these Lagrangians. For example, there is this term that says that the axion field, shown by letter A here, can interact with the electromagnetic fields. So basically axion photon interaction, and most of current searches are based on this particular type of interaction, axion photon interaction. Now, the axion was introduced in quantum chromodynamics, and so it also interacts with gluons, and this term stands for the axion interaction with the gluon, and we are going to use this term in the Hamiltonian in our Kasper electric experiment. Finally, there could also be another type of interaction that's called the derivative interaction, which contains not the field itself, but its relativistic derivative here. And this produces a quasi-magnetic field that can rotate spins of particles. And this is the interaction that is used in the Kasper and Gnome experiments. So before I describe those, let me show you this kind of diagrams. This is a typical diagram that's shown in this field, and what you have here is the axion mass, usually given in a logarithmic scale, and here is the strength of the coupling constant, and in this case, this is the axion photon coupling. What you see here is this is where the so-called canonical axion resides. This is the axion that solved the strong CP problem. And this shows various limits from different experiments. Now, the experiments sometimes are really funny that look for axions. Like this LSW stands for light shining through the wall. And the idea is that if I take a laser and put it onto a wall, the light will not go on the other side. But if I put a very strong magnetic field and also maybe a power build-up cavity to make my photon bounce many times, I can hopefully generate some axions. Axions interact with matter very weakly. They will go on the other side of the wall. Now I have to detect them on the other side. So I make another big magnet there and another power build-up cavity that then should be accurately matched to the cavity on this side, and then I can hope to detect photons in the other cavity. So this is this type of experiment. Now, another interesting type of experiment is where you subcontract the production of the axion to the sun. This is, after all, an object that has a lot of photons and a strong magnetic field. And such experiments are called helioscopes. They look for axion from the sun, and an example here is the CAST experiment at CERN and so on. Actually, on the next slide, sorry about that. On the next slide, I would like to show you the future of the helioscopes. This is a big international project. This is still in the planning stage. This is called IAXO, International Axion Observatory. And the scale here is, you can see the person is about 25 meters or so. And there is a 4.5 Tesla magnet that is designed by the same people who designed the magnet for the Atlas detector. So it's a large volume detector. And there are some photon detectors, so the axions come in, convert into photons, and they are detected here. Then there is the next type of experiments. that actually looks for dark matter directly. And in our galaxy and in all other galaxies, dark matter distribution is broader than the mass, the visible mass distribution. And so it is said that the axions reside in a galactic halo. So experiments looking for these halo axions are called haloscopes. And here, I guess a flagship experiment is at the University of Washington. It's called the ADMX experiment. And the idea here is the following. So you have, again, a magnet and a microwave cavity, and then the halo axion comes in, interacts with a strong magnetic field, and produces then a microwave photon whose frequency is equal to the mass of the axion, and then you measure this at 10 to minus 23, 26, whatever, watt excess of power, and then that will be your detection of the axion. And the beauty, let me show you this one. Once again, the beauty of the ADMX experiment, and also several experiments that are following here, for example, an experiment in Korea and ADMX high frequencies, that these are actually reaching the most interesting range here, which are the which is the range of the QCD axion. Let me now tell you about our Kasper experiment. This is a brainchild of two theorists, Peter Graham and Surjit Rajendran, and the experimental proposal was formulated by Alex Sushkov and Michael Ledbetter. And Alex Sushkov is now leading the Kaspar electric experiment at Boston University. So let me just give you some basic ideas about this. This is based on a model that if axion exists, it was likely produced in the early universe away from the minimum of its potential, and because the axions interact very weakly with everything else, this oscillation can still persist today, and the frequency of the oscillation is given by the mass of the axion. And so if we assume that the dark matter is in fact the energy of this oscillation, we can deduce a lot of properties of the axions. The frequencies that we are going to be interested in this experiment are relatively low frequencies, from kilohertz to gigahertz. Like I mentioned already, the axions lead to time varying CP odd moments, like nuclear moment and sort of a related quantity called the Schiff moment. And we search for these in the Kaspar electric experiment, and the derivative interaction we search for in the Kaspar wind experiment. Now, just from the fact that these axions are supposed to be dark matter in a galaxy, we can say that they should move with speeds on the order of 10 to minus 3 c. That's called virialized velocity. And the basic idea here is that if they moved faster, this would exceed the escape velocity in the galaxy, and they would fly away. Sorry, I keep turning it off. So from this, we, like I said, can deduce a lot of things about this axion oscillation. And one key idea that I would like to mention is in order to for the axions to account for all the dark matter, we have to have a lot of them. And these are bosonic particles. So in some sense, it is better to not think about axions even as individual particles, but instead as a sort of a classical oscillating field. So we can talk about the coherence time of this oscillation, and from this we immediately deduce that we are talking about something that has a Q factor of about 10 to the 6, and we use this in our experiments. All right, so the Kaspar experiment is very similar to your classic CW NMR experiment, where you have nuclear spins that are polarized along a magnetic field, and then you have an additional transverse field that is oscillating. And normally this field has very little effect on my spins, except when the oscillation frequency is close to the Larmor precession frequency. And then such field induces spin precession outside of the, away from the initial polarization direction. In these experiments, what we do is replace this transverse field in an NMR experiment either with the quasi-magnetic field that's produced by the gradient of the axion field, that's the wind experiment, or we want to have a static transverse electric field, and then the term that Professor Gabriel described in his talk just before, D dot E, which oscillates in this case and has the same effect as transverse magnetic field. Then we can pick up the oscillation with, for example, a sensitive squid magnetometer. So this shows the team in Mainz that's working on the Kasper wind experiment. And here are some projected sensitivities. So this is, in this particular case, this is the Kasper electric. This is the QCD axion. And we have some ambitious plans of reaching the QCD axion line in a few years. And this is Kasper wind. In this case, unfortunately, we don't see how to reach the QCD axion line in the near future. But the good news is that theorists are telling us that this region is still very highly theoretically motivated, and is likely that dark matter resides in here. And the good news then is that when we do experiments right here in this corner, we can already start setting limits pretty much now. And we call this Kasper now. This the idea here is that we take the existing experiments and sort of retool them. And there's a lot of different groups that are trying this. And, here is an example. This is a group of Professor Trams at PTB Berlin. This is a big magnetic shield over there. And he has spin polarized xenon and helium and very sensitive magnetometry here. And so he's supposed to submit a paper on some new results anytime now. So this is, again, the Kasper team in Mainz, and this is the new Helmholtz Institute building. We're supposed to move there in a couple of weeks. We have various components of the Kasper wind experiments coming together. Here is just one of them. This is the Zenon hyperpolarizing machine. This is a 100-watt laser that drives a rubidium transition for spin exchange optical pumping. And this is all coming together, but I don't have results to present to you yet, but we hope they will be forthcoming soon. So instead, let me move to another story. And this is sort of another model for dark matter and even possibly dark energy, which is that in this case, we are talking about axion-like particles that do not oscillate in time, but when they were formed in the early universe, they could have, there are certain allowed values of this field, and these values could have been different in different parts of the universe. So this picture is similar to, say, magnetic domains in ferromagnetic materials. And an interesting thing here is that the energy of the field inside the domain is very low, and sort of dark matter is actually the energy in the transition region, in the wall. So if you think about it, it could be like the energy is contains in the tension in the wall. And how do we detect them? The wall has a large gradient of the axion field, so it produces a quasi-magnetic field, just like the wind effect. And so we could try to set up some devices like magnetometers for this, or quasi-magnetometers, I should say, and look for these. But if it is a wall that is going to cross the Earth, it's going to be some sort of a transient effect that is going to be very difficult to identify in a single device. So instead, we use a network of synchronized and correlated sensitive magnetometers of different types. And we coordinate their timing with the GPS. Here's an example of a magnetometer at Mainz. This is a multi-layer magnetic shield enclosure containing one of such magnetometers. And in fact, if you go to our website, you will see a picture of all the stations in different parts of the world. So I took a bad time to take this image because only 2 stations were operational. But on July 28th, we are planning a coordinated run where most of these things will be green, actually. And we are also extending this from magnetometers to also other things. For instance, following this idea of the global network of magnetometers, Andrei Derevyanko and Maxim Pospelov proposed a network of clocks looking at somewhat different kinds of dark matter interactions. And in fact, Andrei presented a nice, actually a couple of posters yesterday, and he gave me these beautiful slides. So the signatures are really amazing. So if you have some sort of a wall that is crossing the Earth, and you have 2 separated clocks, when the wall reaches the first clock, it advances its phase, and so you have, say, 2 synchronized clocks, and then they get out of synchronization, and then when this topological defect reaches the other clock, they're back synchronized again. And so this is attracting a lot of attention. Andrei is leading the collaboration that is using the GPS as a dark matter detector. And in fact, we have a lot of clock groups that are joining now our GNOME network. So it's now really not a magnetometer network, but a network that combines a lot of different sensors. Now I have to move very quickly because I have only 2 minutes left. There are things that could be dark matter beyond axions. And there's a beautiful idea several years ago put forward by Asimina Arvanitaki and her students that the particle called the dilaton could also be dark matter. And this is not a pseudoscalar like the axion is, but a scalar field that arises in some string theory models. And what they predicted is that this could cause, in fact, oscillation of fundamental constants that can be detected with atomic clocks. Now, in our group, we have a device that is a very bad atomic clock, but it's an okay differential atomic clock. It's like two atomic clocks in one. This is the dysprosium atom, and in fact, we built an apparatus, and it's listed in the university bureaucratic papers as a device called alpha variometer, the device that measures the variation of alpha. And we've done a lot of different experiments with this system, and you will hear about some of them in the next talk by Professor Hafner. Okay, that's the Lorentz invariance, in fact. But we were able to use this apparatus to look for dilatons, and we improved certain limits by many orders of magnitude. But I don't have time to talk about this at the moment, because I would like to tell you, the chairman is coming up. I would like to take 10 seconds to tell you about the latest thing that you can find on the archive. One type of axion search that I did not tell you about in the beginning when I gave you the map of searches is that if an axion exists, it could cause a sort of virtual axions could modify how things interact. It could be a fifth force source, or it could also change the value of fundamental constants in the presence of massive objects. And so here is our alpha variometer, and here is 600 pounds of lead. And we very carefully suspend it in one point in the lab, so when we move it up and down, we don't change the stresses in the building. And here is our alpha variometer, and we see if alpha is changing. And it didn't change. The dysprosium frequencies remain constant to within about 300 millihertz or so in this experiment. So we combined this with the gravitational, with the mass of the other sources like sun and the moon. And we were able to put limits on various constants describing these exotic axion interactions. Some combinations are unique to this approach, and some combinations are a little bit worse at the moment compared to various fifth force measurements. But people with good atomic clocks can do what they did in the past with our dysprosium results. They can very quickly improve on them. So I would like to therefore advertise our paper on the archive. All right, so I gave you a long introduction, and also spoke about the experiments that we are doing. And the one last thing I would like to say is that a lot of us for many years have been doing sort of some experiments that appeared already in the maybe very first proceedings of ICAP, measuring EDMs, measuring parity violation, and so on. But I'm quite excited that I think now these ideas from the dark sector, so to say, dark matter and dark energy, they provide new motivations to do these experiments and interpret them in different ways. Thank you.
Okay. Any questions? Okay. I think we could take about one, maybe two questions. Okay, yeah, please, yes, yes, yes.
So you showed those results with dysprosium.
For the mass sourcing? Yeah. So let me go back. So this was our dysprosium result for the dilatons, which is also oscillating alpha. And then there is a very recent result from Paris, from the third group, that used 5 years of the cesium-rubidium clock comparison. And in the region where we overlap in the mass region, they have pretty similar constraints that can be improved in the future, I think. But they had a 5-year data set, so they 5 or 6 year data set, so they could do better. So basically, I say anybody who has a differential clock at 10 to minus 16, a few times 10 to minus 17, can do better than us.
Okay, just one more question, maybe. Well, I mean, if not,
Hello. So, how long the lifetime of the axion? Is it the lifetime?
The lifetime of the axion is many lifetimes of the universe. So they don't practice. Well, for our purposes, they don't decay.
okay, I think we should move on. I mean, before that, I mean, let's thank Professor Budker for talking about experiments that could have very far-reaching implications in the future. Okay, the next speaker is Hartmut Hefner, and the title of his talk is a Michelson-Morley test for electrons using trapped ions.